Greetings, AP Calc BC students. Mr. Record here from Avon High School. Going to take a look at our fourth example from our fictitious topic 8.14, all about finding work. Not a tested topic on the Calc BC exam, but a very important part of a Calculus 2 course at the college level. So we are going to launch a satellite up into space. That sounds like a good time. So in order to do something like this, what we're going to have to do is we're going to have to understand some of the wonderful contributions that one of the most brilliant minds of antiquity has left with us, and it's the Renaissance mathematician and scientist Isaac Newton. And Isaac Newton had developed several laws of gravitation, but his specific law of universal gravitation is the one that basically says that the weight of or force upon a body will vary inversely as the square of its distance from the center of the earth. And you can really apply this to many different kinds of situation, whether it's the earth and the moon, the earth and other planets around it for that matter, and certainly the earth and some kind of a sort of vehicle that is allowed to kind of launch into the upper extremities of the Earth's atmosphere. And that's the example that we're going to take into consideration here. Now, that law basically says that F is equal to G, which is our gravitational constant, times the product of the mass of the two particular items. So we could say the mass of the Earth and the mass of, say, a satellite that we're launching. And then we just simply divide that by the square of the distance between the two objects. Now, to make this problem a little bit more simplified in our realm, we're going to go ahead and say we're going to compute the G times the product of the masses, and that's going to produce another singular constant, C. And so we're going to kind of move out of the realm of using mass and kilograms and the gravitational constant, and we're going to stick with our typical, imperial units, in this case of miles and pounds, and call this C over x squared. So in our particular example, the weight of a body varies inversely as the square of the distance from the center of the Earth. So there you go. That's just recapitulating our particular formula. F of x is c over x squared. Let's say that we have a satellite that weighs 1,000 pounds on the surface of the Earth. If we assume that the radius of the Earth is 4,000 miles, which has been rounded a little bit, how much work is done to propel that satellite into orbit at an altitude of 12,000 miles? Well, our first task is to use the data that's given so that we can compute this constant, this value that's associated with the G times the sum of the masses. And so to make that happen, we can use the fact that the force that we're going to employ is 1,000 pounds, and that the distance between the two objects is found by using the idea that the radius of the Earth is 4,000. Okay, so we're using this idea that this particular satellite is sitting right here on the surface of the Earth, right? We're gonna launch it from, looks like from Africa there, right? And so from the center of the Earth to the launch point is measured as 4,000. Now notice we are always measuring things back to the center of the Earth to make this happen. Now you really don't need a calculator to pull this off. 4,000 squared turns out to be 16 with 6 zeros. So that would be 16 million. And if we multiply that by another 1,000, we're going to place 3 more zeros. And so we essentially have we have 16, and 1,000,000 times 1,000 is just going to make a billion. So that's 16 times 9 zeros. Now, it's going to get awfully awkward to continue to write 16 billion many, many times over again. So we're going to use our handy scientific notation advantage and call this 1.6 times 10 to the, and I believe that would be to the 10th power, right? We're going to move that decimal point to the left 10 units. Now that's going to be our C that we're going to be able to use throughout the problem. Now part B asks us to write and evaluate an expression that will represent the amount of work to propel that satellite from the surface to a height of 12,000 miles. And so for that work setup, we will be integrating, and we will integrate this particular expression, c over x squared, now that we know the c to be 1.6 times 10 to the 10th. There's our denominator, x squared, doing so with respect to x. Now this part could be a little tricky. Think about where you're launching the satellite, what would be the distance, measure to the center of the Earth, and that of course would be 4,000. And if we want this thing to reach a height of 12,000, that's 12,000, right? 12,000 miles from the surface of the Earth. And I do want you to kind of forgive me a little bit. I'm using a unit of m, which can very easily be construed as meters, but in this problem, the m is going to stand for miles. So if I start at the center of the Earth where all of my measurement has taken place, I have to make sure that my upper limit of integration is 16,000. Sometimes that's really tricky for kids because we have to measure things from that sort of focal point of where all the gravity is sort of being directed towards, and that would be the core or the center of the Earth. This is not a very difficult integral to enter into a calculator, nor is it very difficult to solve by pencil and paper. The only problem is that you probably would need a calculator by the time you inserted these very hideous looking boundaries. So for the purpose of making the problem go a little smoother, use your TI calculator or your Hewlett Packard or Desmos or whatever, and if all goes well, you should get an answer of 3 million for this definite integral. 3 million, and the units would consist of a linear measurement of miles and a force measurement of pounds. So mile pounds is going to be our measurement here. Now, if we move to part C, the question is now how much work is necessary to lift the satellite to a height of 60,000 miles. So now what's going on is this thing is going to be moving way into the upper parts of our atmosphere, way beyond our atmosphere for that matter. And I would say at 60,000 miles, we can say that we're in our what we would call our deep space. All right. And so to make that happen, we're going to go ahead and set up the work again, and we will use the exact same formula. It's going to be our 1.6 times 10 to the 10th over x squared. We're going to find this antiderivative with respect to x. But this time, we read this, how much work is necessary to lift the satellite to a height of 60,000? What percentage of the total work necessary to propel the satellite to that height does this represent? Well, if we're already thinking about using our answer for 3 million, so let's just approach this problem from the standpoint of we're leaving off with our work that we've done before. I think we could do that. Let's call this a lower boundary of 16,000. And then our upper boundary for 60,000 miles, remember that's 60,000 miles above the surface of the Earth. So in order for that to be construed as above the core of the Earth, that's going to be 64,000 miles. Now, once again, this is a very easy antiderivative right? If we just use our graphing calculator, push the right buttons, we should end up with an answer of 750,000 mile-pounds. Now you might ask, why on earth did I want to calculate this starting at 16,000? Because I could have calculated it starting at 4,000, and that's probably what I should have done to answer the question. But I wanted to show you something absolutely mind-boggling. In order to get this satellite off the surface of the Earth to this seemingly shorter distance above the Earth's surface, 16,000 miles isn't short by any means, but we got 3 million mile-pounds of work to sort of invoke into this launch and this propelling of the satellite. But if we wanted to take that an additional several thousand more miles high, notice that it's not going to require nearly as much work. And that's where this idea of the Newton's law of universal gravitational comes into play. Because by the time that we are so far from the Earth and we're in space, we don't have to exert nearly as much force because there's just very little to no gravitational pull at that particular time. Okay? Now, to answer this question here, it says, for the total amount of work that's required, I guess, we probably should add these numbers together, right? The answer from part B rather, and the answer from part C will really depict the total amount of work to take it all the way up to that 60,000. Now, if we want to figure out what percentage of work was necessary just to propel the satellite to this height, then we could say that, well, we got the 750,000, right? That's going to take it just from 16,000 to 64. And if we divide that by the original 3,750,000, that's the total work to get it from the Earth's surface to that 60,000 mile distance above the Earth's surface. In a calculator, this is going to give you 0.2. That's 20%. And so you can see that only 20% of the amount of work is required to take it this longer distance. Now for part D rather, if H represents the height above the Earth's surface to which we wish to propel the satellite, find the limit of the amount of work as H approaches infinity. And so what we're looking at doing here is essentially integrating from 4,000 rather, right? We're going to go from the surface of the Earth to essentially infinity. That's what our goal is. And we still have our formula, 1.6 times 10 to the 10th over x squared with respect to x. Now, really, this is another version of an improper integral that, as we will later study, that we really would have to set this up as a limit where we would use some arbitrary variable for this upper boundary so that we could sort of trick it into becoming infinity. So I would put a b up there as such, and then we would go ahead and use the properties of solving an improper integral, which is something that's discussed at the end of Unit 6 in the College Board course and exam description. But again, what I'm going to do is I'm going to rely on our graphing calculator one more time to take this into consideration. And so we'll pull up that calculator. He is our good friend. I'll delete anything that may have been in there from a previous problem. And we're going to go ahead and set this up. Shift plus, integrate from 4,000 all the way up to infinity. And then our integrand is 1.6 times 10 to the 10th. That's going to be this EE button here, and then I can just type a 10, and that is times 10 to the 10th power, all divided by x squared. All right, let's see. Let's take this thing way up into the outer part of the solar system, the outer part of the Milky Way galaxy, into the next galaxy, the galaxy after that, and let's keep this thing going on forever. And interestingly enough, the answer is 4 times 10 to the 6th power. That's 4 million. So it seems like if we were to rely on this principle, then it wouldn't take that much more work to send this into an infinite sort of trip. What? Only 3,000 mile-pounds would take it up to 16,000 miles. An infinite number of miles is just another 1,000 mile-pounds. So why not? Right? We should be visiting the far edges of our entire universe if that's the case. Well, obviously there are limitations on this, and Newton's law of universal gravity probably does have some limitations the farther that we were to extend it. And so a lot of times these rules have certain domains for which they're only going to be applicable. But I thought that the math behind this problem was still kind of interesting nonetheless. So here it is, your example using Newton's universal law of gravity to compute the work to send a satellite up into space. A couple more examples still coming your way. Be sure to check those out.